everyone. So in this video, we're going to be learning a new method for evaluating integrals called trigonometric substitution. So the main idea behind trigonometric substitution is that we're going to start with an integral that does not have any trig functions in it. And we're going to actually introduce a trigonometric function into the integral. And so at first, it's going to seem kind of counterintuitive because it's going to look like we're making our function more complicated, our integral more complicated. But basically, it will allow us to take advantage of some of the trig identities to ultimately simplify our integral and be left with an integral that we know how to evaluate using the methods that we talked about in the last two videos. So we're going to start with an integral that's not a trig integral and basically turn it into a trig integral. And we'll see how, that will basically use some of the methods we talked about in the previous two videos. So I just want to start by reminding you of some of the integrals that you should just kind of be aware of as kind of integral table integrals. And I wanted to add a few to the bottom, or I did add a few to the bottom. So last time we stuck with ones that were about sine, cosine, tangent, and secant. And I just wanted to show you there's a few others that I added here. So cosecant squared, the antiderivative of that is negative cotangent. Cosecant times cotangent, the antiderivative is negative cosecant. So that's just because the derivative of cotangent is negative cosecant, and the derivative of cosecant is negative cosecant cotangent. And then these next two are a little more complicated. You would have to actually kind of go through a process to find these. But the antiderivative of cotangent is ln of absolute value of sine of x. So if you wanted to show that one, you could do it by rewriting cotangent as cosine over sine and using a substitution. And then the antiderivative of cosecant is ln of absolute value of cosecant of x minus cotangent of x plus c. So the reason I'm just reminding you of these again, it's not that, I want you to memorize these or anything, but what you do want to kind of have in mind is which ones are on this table, right? Or just have some kind of awareness, because what's going to happen on some of these integrals is, maybe you'll go through the process and you'll do some simplification. And let's say you get to the point where you're left with the integral of cosecant squared of x dx. You want to be able to recognize that you're done at that stage, right? You want to be aware of which things are on this list, because those are the ones that once you get to that point, you're done with the kind of hard work and you can just look up what the antiderivative is. Okay, so before we get into our first example, I also just wanted to quickly remind you of the different Pythagorean identities, because these are going to be coming up in this video as well as the next video. So we talked about these in a couple of videos ago, but basically we have kind of the most important one, or the starting point you can think of, is sine squared of theta plus cosine squared of theta is equal to 1. And so if you take this identity and you divide everything by cosine squared, that gives you another identity, which is tangent squared of theta plus 1 is equal to secant squared of theta. So that one we used in the last couple of videos as well. But there's one other. So if you start with sine squared of theta plus cosine squared of theta equals 1, and you divide everything instead by sine squared of theta, that will give you the identity 1 plus cotangent squared of theta is equal to cosecant squared of theta. So that's it's not going to come up quite as much, but you want to be aware of that one as well. And I'm not sure exactly yet which identities I'll give you on tests and stuff like that, but I would say, at least for me, I just tend to memorize this one. And if you have that one memorized, then you can just get the other two from it relatively easily. So I want to start off with an example just to kind of let you see how this process works, and then we'll write down some kind of general rules of how this is going to work. And then after that, we'll do a couple more examples. So the integral I want to start with is the integral of square root of 1 minus x squared divided by x squared dx. So looking at this kind of in the way that we've looked at integrals in previous sections, you might guess that we could do the substitution u is equal to 1 minus x squared. But that's actually not going to work, basically because you would get, du is equal to negative 2x dx, and that wouldn't get rid of this x squared. It just basically wouldn't really work out with this integral. So that's not what we're going to do. And the reason I wrote this down, even though we're not going to use it, is I just want to kind of remind you of how regular substitution works. So with regular substitution, you're taking a complicated piece of your integral, right? Something that is more complicated, and you're replacing it with a single variable. And what we're going to do now is actually going to be kind of the opposite. So what we're going to do is we're going to take x, which is a single variable, and we're going to replace it with a more complicated function. But just kind of trust, and you'll see that even though initially things will look more complicated, it will ultimately help us evaluate the integral. So in this case, we're going to let x equal sine of theta. And then what does that mean that dx is going to be? Well, if you take the derivative of this, you would get dx d theta, because here we're seeing x as a function of theta, right? So the derivative would be dx d theta would be equal to cosine of theta. And so another way of writing that would just be to say that dx is equal to cosine of theta d theta. So before we go ahead with this substitution, there's one little thing I want to point out, and I don't want you to get too fixated on this because it's not super duper important, but it's just kind of a technicality. So when you make a substitution like this, so x is equal to sine of theta, it's important that there is a one-to-one correspondence between x and theta. And so what I mean by that is we want to ensure that there are not multiple values of theta that correspond to the same value of x. And so if we did not place any restrictions on what angle theta is, then actually that would not be true. We would have multiple values of theta corresponding to the same value of x. So I just want to quickly show you a graph to kind of let you see that. So here's the graph of sine of theta. And so we're making the substitution x is equal to sine of theta. So that means that x is our outputs, right? I know that's like, we usually think of y as being outputs, but in this case, if we're saying x is equal to sine of theta, that means that x represents the outputs of the sine function. And so the sine function repeats itself, right, infinitely. So that means that for every different possible output, there are lots of different angles that give you that output, infinitely many angles that give you that same output. And so in order to kind of prevent that from happening, what we can do is restrict theta to being just between negative pi over 2 and positive pi over 2. And that's the same restriction that you do when you're doing inverse sine. So if I restrict sine to just being this little piece of the graph, well, we've really captured all of the shape of the graph, right? Because it goes through all the different heights, but it doesn't repeat itself. And so this is just something, you don't really need to write this down. It's kind of something that's just assumed. But when you make this substitution, you're really kind of implicitly assuming that theta is between negative pi over 2 and pi over 2. Okay, so let's see what our integral becomes when we make the substitution. So we're going to end up with the integral of the square root of 1 minus sine squared of theta. And then in the denominator, we have sine squared of theta. And then the dx becomes cosine of theta, d theta. Okay, so as stated, this now is a much more complicated looking integral. However, we can now take advantage of trig identities. So 1 minus sine squared of theta, that's the same thing as cosine squared of theta, right? And so that means that if we're taking the square root of 1 minus sine squared of theta, like we have in our integral, well, that's the square root of cosine squared of theta. So technically, the square root of cosine squared of theta is actually the absolute value of cosine of theta, right? And so it's the same thing, like if you take the square root of a squared, that's equal to absolute value of a in general. And that's just because you don't know whether your original number was positive or negative. And so when you square it and then take the square root, you're guaranteed to get a positive result. So it might not match up with your original number. So technically, square root of cosine squared of theta is actually absolute value of cosine of theta. However, because of this restriction we placed on theta, it turns out that cosine happens to be positive. So let's just look back at this graph for a second. So we chose to make sine of theta, or we chose this restriction on theta so that sine of theta would be 1-to-1, so that we would have this kind of representative snippet of the graph. But if we look at cosine of theta and we take that same restriction on theta, well, now cosine is always positive. And so it just kind of works out that the restriction we had to do to make the sine thing work out also happens to make cosine be positive. So in other words, we basically just don't have to worry about this absolute value. We can just say, okay, it equals cosine of theta. And that's because theta is between -pi/2 and pi/2. So again, I wouldn't really worry about this. It's not something that you have to like write down every time or anything like that. It's just something to kind of be aware that it's going on in the background. I would just feel like I was lying to you if I didn't tell you this detail, but you don't really need to worry about it when you're actually doing these integrals. And so that means that our integral actually comes out to be the integral of cosine of theta over sine squared of theta times cosine of theta d theta. Okay, so now let's rewrite this as the integral of cosine squared of theta over sine squared of theta d theta. And so another way of writing cosine squared over sine squared would be cotangent squared. And so this might be a point at which you would go and look at your integral table and kind of see like, okay, where am I at with this? What do I know? So we don't have an antiderivative for cotangent squared, right? But we do have one for cosecant squared. And if we go back to our top of our page here, we have this identity that relates cotangent and cosecant, right? So if we want to kind of go from cotangent to cosecant, we can rewrite this as cotangent squared of theta is equal to cosecant squared of theta minus 1. So now we can go back to our integral and rewrite this as the integral of cosecant squared of theta minus 1 d theta. And then that allows us to now evaluate two separate integrals. So we're going to have the integral of cosecant squared of theta d theta. And then we're going to have minus the integral of theta, or sorry, of 1 d theta. Okay, so what does this give us? Well, we just saw on the previous page that the antiderivative of cosecant squared is negative cotangent. So we have negative cotangent of theta. And then the antiderivative of 1 is theta. So we're done with the integration part, but we're not done with this problem, right? So why are we not done with this problem? Well, the integral was originally given to us with its variable being x, right? And it's an indefinite integral. So just like with the substitution that we did earlier with u, you have to go back to x. Same deal here. We have to go back to x if it's a indefinite integral. And so the way that we can do this is basically we want to go back to our relationship here. We know that x is equal to sine of theta, and we're going to use that to actually draw a right triangle that will then allow us to express everything else in terms of x. So just like I would like to mention this sometimes with regular substitution, you don't want to think of x is equal to sine of theta as like a one-time thing. You want to think of this as this enduring relationship between x and theta. It's the way that you can always translate between x and theta. So we're going to go and we're going to take this piece of information down here. So we know that sine of theta is equal to x, and let's actually rewrite that as x over 1. Right? Because x is the same as x over 1. And so using this information, let's draw a right triangle with an angle of theta. And so one other thing I should say here is that when we draw this triangle, we're kind of assuming that theta is actually not just between negative pi over 2 and pi over 2, but between 0 and pi over 2. But basically, even if you couldn't actually draw the triangle, so even if theta turned out to be a negative angle, you would still get the right thing. So again, just don't worry about it too much. You know, maybe know that when you're drawing the triangle, you might be slightly kind of, I don't know, glossing over some detail, but just trust that when you draw this triangle, it will lead you to the right answer. You don't need to worry about whether theta was a positive angle or not when you do this. Okay, so what does it mean when we say sine of theta is x over 1? Well, sine is equal to opposite over hypotenuse, right, in a right triangle. And so that tells us that the opposite side of this triangle is x, and the hypotenuse is 1. And then how can we find this remaining side? Well, we can just use the Pythagorean theorem. So if you use the Pythagorean theorem, so maybe let's call this missing side here, we could call it, let's just say b. So how could we find b? Well, we can say b squared plus x squared is equal to 1. And so that tells us that b is equal to the square root of 1 minus x squared. So now we can fill in this side with the square root of 1 minus x squared. Okay, so why did we do this? Why is this useful? Well, now we can express cotangent of theta using the sides on this triangle, right? So cotangent of theta is going to be equal to, so we're going to have a negative sign, but then cotangent of theta. So what's cotangent? Cotangent is equal to the reciprocal of tangent. So instead of being opposite over adjacent, it's going to be adjacent over opposite. So maybe let me actually write this down so that in the notes it will make sense. So what we're doing here is we're taking cotangent of theta. To figure out what that is, we're doing adjacent over opposite. And that is equal to the adjacent side to theta is the square root of 1 minus x squared. The opposite side is x. And so we can put in for cotangent, we have this negative sign, and then we have the square root of 1 minus x squared all over x. Then we have theta. So how can we express theta in terms of x? Well, we know that sine of theta is x, right? So if sine of theta is x, then that means that theta is inverse sine of x. And again, that's actually where that domain restriction comes in. So because we know that theta is between negative pi over 2 and pi over 2, then we can truly say that theta is the same as inverse sine of x, because inverse sine has a restricted range. Okay, so now we can, instead of writing theta here, we write inverse sine of x. And then we have plus c, and that's it. Okay, so let's recap. What did we do here? And then we'll get into some kind of general approaches and another example. So what did we do? We replaced x with sine of theta, right? And then that allowed us to use an identity and replace 1 minus sine squared of theta with cosine squared of theta. And it basically served to get rid of the square root. That's really kind of the main reason for using trig substitution, is it gets rid of your square root. Then we just evaluated the remaining integral normally. And then the only kind of different step at the end was we needed to figure out what cotangent of theta and theta were in terms of x. And so in order to re-express cotangent of theta in terms of x, we drew a triangle that allowed us to take this piece of information, that sine of theta was x over 1, and kind of rearrange that information to figure out what cotangent of theta was. Okay, so actually, I'm going to write down the next example, and then we'll write down the general approach. I just want to have another example to kind of point at so that when I get to the next part, it will make a little bit more sense. So the next example we're going to look at is going to be the integral of x cubed times the square root of 4 minus x squared. So what's different about this one compared to the other one? Well, a few things, but the thing that is important here is that instead of it being 1 minus x squared, now it's 4 minus x squared. So what substitution can we do that will still allow us to take advantage of the identities we know? Well, if we were to let x equal sine of theta, so let me just kind of write that down even though that's wrong. So if we just let x equal sine of theta, then we would end up with the square root of 4 minus sine squared of theta. And that's not useful. There's no identity that says what the square root of 4 minus sine squared of theta is. That's not a thing. So that's not helpful. What would be helpful is if we had 4 minus 4 times sine squared of theta. Why would that be useful? Because then we could rewrite that as the square root of 4 times 1 minus sine squared of theta. And then we could actually pull that 4 outside and have 2 times the square root of 1 minus sine squared of theta. And then we would be in the same position that we were on the previous example. So what substitution would we need to do in order to get a 4 sine squared of theta here? Well, it wouldn't be 4, it would actually be 2, right? We would want to let x equal 2 times sine of theta, because then when we square it, we'll get 4 sine squared of theta. So basically, what this tells us is that in general, if your integral contains an expression of the form square root of a squared minus x squared. So the first example we did had 1 minus x squared. The second example has 4 minus x squared. It could also be 9 minus x squared, 25 minus x squared, anything squared minus x squared. We're always going to use the substitution did I put too many? Substitution. I always doubt myself, my spelling sometimes. We're going to use x is equal to a times sine of theta, because that's what will allow us to then we'll end up with a squared sine squared of theta, and we'll be able to factor out that extra a and pull that outside of the square root. Okay, so that's the first thing we need to know. We're going to use the substitution x is equal to a times sine of theta. And then what else are we going to use? We're going to use the identity square root of 1 minus sine squared of theta is equal to cosine of theta. And so maybe let me just add in that domain restriction, even though I said it's not super important. I'm still going to write it down here. And then basically from there, it's just a, you'll be left with a trig integral, and you can use the approaches that we saw in the last few videos. So I just want to mention that in this video, we're going to be focusing only on the substitution x is equal to a times sine of theta. So we're only going to be looking at examples where we have a square root like this. But in the next video, we're going to be looking at examples where you use actually a different trig function as your substitution. So that's why I'm writing this down almost like it's going to be a list. This is kind of like to be continued. So maybe I'll even write that down. So there's going to be other kind of formats and other substitutions, but just to kind of keep things simple, I just wanted to start with one possible substitution in this video. Okay, so let's get back to this example. So we're letting x equal 2 times sine of theta, and so that means that dx is going to equal 2 times cosine of theta d theta. Okay, so let's see what our integral becomes when we make that substitution. So we're going to end up with, so we have 2 times sine of theta cubed. So that's going to give us 8 times sine cubed of theta. And then inside the square root, we're going to have 4 minus, so when we take 2 sine of theta and square it, we'll get 4 sine squared of theta, d theta. Oops, not d theta yet. This is, I think, the most common mistake you can make on trig substitution is forgetting to put in your dx. So our dx included 2 times cosine of theta d theta. Okay, so let's start to simplify this. So we have the integral of 8 times sine cubed of theta, and then we can factor out a 4 from both of these, right? So we can rewrite this as 4 times 1 minus sine squared of theta times 2 times cosine of theta. And we're going to pull out the constants outside of this integral. Let's just wait until we kind of have them all ready to take them out at once. So now we have the integral of 8 times sine cubed of theta. And now we can bring this 4 outside of the square root. And so square root of 4 is 2. And so we're left with 2 times the square root of 1 minus sine squared of theta. And then we have another 2 times cosine of theta, d theta. And so altogether we have 8 times 2 times 2, so that's going to be 32. Okay, so now we have 32 times sine cubed of theta, and then we saw earlier that, square root of 1 minus sine squared of theta, because of our restriction on theta, that's just equal to cosine of theta. And so we can replace that whole thing with cosine of theta. And then we have another cosine of theta, d theta. Okay, so what does this give us? Well, this is sine cubed of theta times cosine squared of theta. So this is the type of integral that we were doing, not necessarily in the last video, but like 2 videos ago, right? We were doing these integrals where you had different powers of sine and cosine being multiplied together. And so what you might remember from that is that if you have an odd power of sine or cosine, that allows you to kind of pull one copy of sine or cosine aside and then use it to do a substitution. So we're actually, we've already done one substitution, right? We've substituted in sine of theta for x. Now we're actually going to do another substitution. So we're going to change variables again to, let's use u. So first, before we do that, let's actually rewrite this as, so we want to separate out one of the sine of thetas. So basically, remember, whichever of your 2 sine and cosine is odd, that's the one that you want to pull one copy aside. And so this sine of theta, d theta, that's what's going to be the derivative of our substitution. So that kind of tells us that the substitution we're going to make is going to be u is equal to cosine of theta, because that's what will allow us to get rid of this extra sine of theta when we do that substitution. And so because we're trying to do the substitution where we let u equal cosine of theta, that tells us that we want to actually rewrite sine squared of theta as in terms of cosine, right? So we're actually going to use kind of the same identity, but in a different way. So we're going to use the fact that sine squared of theta is equal to 1 minus cosine squared of theta. Okay, so that's going to give us now 32 times the integral of 1 minus cosine squared of theta times cosine squared of theta times sine of theta d theta. And so this is where now we can make that substitution like we did in those other videos. So we're going to let u equal to cosine of theta, and then du is equal to negative sine of theta d theta. And so we can then replace all of our cosine of thetas with u. So we're left with 1 minus u squared times u squared. And then the sine of theta d theta, so that basically is going to become du. We just need to then introduce a negative sign out front. So we're going to introduce a negative sign here, and then we can replace that with du. So together, this du and this negative sign work out to give us the right thing. Okay, so let's distribute, and then we'll be ready to take our antiderivative. So we have negative 32 times the integral of u squared minus u to the 4th du. And so our antiderivative in this case is going to be u cubed over 3. And then we have minus u to the 5th over 5. And then we have a plus c. And so altogether, this is going to give us, I'm just trying to think if I should distribute or not. Let's leave it undistributed for now. So let's just leave it like this. Okay, so next we have to go back to, so right now our variable is u, right? So we kind of have two steps. First, we have to go back to theta, because going back to theta will then allow us to go back to x. So let's first start by rewriting this with u equal to cosine of theta. So we have negative 32 times cosine cubed of theta over 3 minus cosine to the 5th of theta over 5 plus c. So now we have our answer in terms of theta, but we still need to go one step further and rewrite it in terms of x. So this is where we go back and look at our substitution. So the substitution we had made was x is equal to 2 times sine of theta. So we have 2 times sine of theta is equal to x. So in other words, sine of theta is equal to x over 2. And so that means that if we draw a right triangle with an angle of theta, then the opposite side is going to have a length of x, and the hypotenuse is going to have a length of 2. So we can go ahead and draw that triangle. So if this is our angle theta, then the opposite side is x, the hypotenuse is 2. And so if you use the Pythagorean theorem, you can find that this side is going to have a length of 4 minus x squared, or square root of 4 minus x squared. Because, yeah, basically if you just label this other side as b or something like that and plug it into the Pythagorean theorem, you'll find square root of 4 minus x squared. Okay, so now we're ready to look at what we actually need in our question. So we're looking for cosine, right? That's the only trig function that we see in our answer. And so we need to figure out what cosine of theta is. And so looking at our picture, we know that cosine is supposed to be equal to adjacent over hypotenuse. And so in this case, that gives us square root of 4 minus x squared over 2. And so now we can put that back in for cosine of theta and rewrite our answer, and it will now be in terms of x. So our answer comes out to be, maybe let me draw an arrow, oops. So we currently have a negative 32 on the outside. I'll leave that factored out and then we can multiply it in at the end. And then we now are going to have this quantity cubed. So we have square root of 4 minus x squared over 2, that whole thing cubed, all divided by 3. And then here we have the same thing, but to the 5th. So square root of 4 minus x squared over 2 to the 5th, all over 5. And then we have our plus c. Okay, so let's clean that up a little bit. So I'm going to leave that negative 32 on the outside for the moment. And so we can rewrite the numerator, we'll just leave it maybe written as that square root cubed. You could rewrite it different ways, but honestly, I think that it looks simpler if you just kind of leave the cube on the outside in this case. So we're going to have the square root of 4 minus x squared cubed. And then in the denominator, that's going to be over 8. And then we're also dividing by 3. And then here we have the square root of 4 minus x squared all to the 5th divided by, so 2 to the 5th power is 32. And that's all getting divided by 5. And so now we can combine those denominators. So we'll have negative 32, and I'll distribute that negative 32 in as well. So we have negative 32 times the square root of 4 minus x squared cubed, all divided by, so when you're dividing by 8 and then dividing by 3, that's the same as multiplying by 1/3. So you're going to end up with 24 in the denominator. And then here we have minus, or actually plus 32 times the square root of, and I forgot the plus c here, sorry, 4 minus x squared to the 5th. And then if we do 32 as our denominator times 1/5, we have 5 times 32, which is 160. And so now things can actually be reduced a little bit because 32 and 24, those are both divisible by, let's see, we can do 8, right? They're both divisible by 8. So this is going to be the same thing as negative 4 times the square root of 4 minus x squared cubed all over 3. And then here, these are both divisible by 16. Actually, I think they're both divisible by 32. So this one is just going to be the square root of 4 minus x squared to the 5th. And then this will be over 5. Basically, we could have done some simplification before multiplying then that negative 32. That probably would have made that last step a little easier. And that's our answer. And like I said, you could, so anytime you're taking a square root and raising it to a power, you can simplify it a little bit because you could say, you know, if you take a square root and multiply it with itself once, that will then get rid of the square root. And then you could rewrite this as 4 minus x squared times the square root of 4 minus x squared. But I just don't think that I think that's going to make this expression actually look more complicated. So next we're going to look at another example. This last example is now going to be a definite integral. So we'll see how things are a little bit different for definite integrals. Basically, in some ways, I think it's actually going to be a little easier with a definite integral. Okay, so in this case, we're going to be integrating now from 0 to 3 of x squared times the square root of 9 minus x squared dx. So this one is another one where you cannot use a regular substitution. It just wouldn't work out. You know, if you tried to let u equal 9 minus x squared, basically you would end up with this extra factor of x when you take the derivative of that, and it just wouldn't, you know, things wouldn't be able to be all converted into u's nicely. And so we are kind of forced to use trigonometric substitution here. So what substitution do we want to make in this case? Well, if we're letting x be equal to, you know, basically we want to end up with something, a coefficient that matches this one, right? So that we can factor out a common factor from both of them and then take it outside of the square root. And so what we want to do in this case is let x equal 3 times sine of theta, because then when we square it, we'll get 9 sine squared of theta. And then that tells us that dx is going to be equal to 3 times cosine of theta, d theta. So just like with regular substitution, we can change the bounds either at the beginning or later on. I think that for this, it's going to be easier to change it at the beginning because basically what we'll see is that it allows us to avoid the stuff we had to do at the end, right? So at the end here, we had to draw a triangle and do all this stuff, and it wasn't like that hard or anything, but it's a little nicer, I think, to avoid doing that by just changing the bounds at the beginning, because then you never have to go back to x. You can kind of keep things in terms of theta. However, it's, you know, it's a little trickier to figure out the bounds. So our current bounds are in terms of x, right? And we want to rewrite them in terms of theta. So the lower bound is 0 is the x value is equal to sine of theta. So we need to figure out what that tells us that theta is. And so this is where, again, that restriction, that theta is between negative pi over 2 and positive pi over 2, that's kind of where that comes in. So what is the only angle between negative pi over 2 and positive pi over 2 where sine of theta equals 0? It's the angle theta equals 0. And then for the, and sorry, actually, I made a mistake here. So really this was 0 is equal to 3 times sine of theta. But that gives us the same thing, right? Because if we divide both sides by 3, we just get 0 is equal to sine of theta. But it is important for this next one. So for the top bound, now we have 3 is equal to 3 sine of theta. And so this tells us that, 1 is equal to sine of theta. And so what does that tell us about theta? Well, that means that theta has to be pi over 2. because that's the only angle between negative pi over 2 and pi over 2 where sine is equal to 1. Okay, so let's rewrite our integral now. So now we're going to have the integral from 0 to pi over 2 so we're going to replace our x with 3 times sine of theta. So we're going to get 9 times sine squared of theta. Then we're going to have the square root of 9 minus 9 sine squared of theta. And then we're going to have, we're going to multiply that with 3 times cosine of theta, d theta. Okay, so let's, again, kind of clean this up and figure out what is the constant that we can pull out of everything. So we're going to have 9 times sine squared of theta. And then here we have, we can factor out a 9 from both of them. So we have the square root of 9 times 1 minus sine squared of theta. And then we have times 3 cosine of theta, d theta. So this is now going to give us the integral from 0 to pi over 2 of 9 times sine squared of theta times, so we can pull out a 3, times 1 minus sine squared of theta, and then we have another 3 here times cosine of theta. Okay, so altogether, what is that? Well, we have 9 times 3 times another 3, so that's going to be a total of 81 that we can take out of this integral. So we have 81 times the integral from 0 to pi over 2 of sine squared of theta, and then 1 minus the square root of 1 minus sine squared of theta. That is going to give us cosine of theta. So now we have sine squared of theta times cosine of theta times another cosine of theta. Okay, so that is the same thing as 81 times the integral from 0 to pi over 2 of sine squared of theta times cosine squared of theta. All right, so how do we do this integral? Well, we don't have an odd power of sine or cosine, right? Like they're both even. And so that approach of kind of pulling one of the sines or cosines aside and using it for a substitution isn't going to work. And so I can't remember if I did this example in our video or maybe if it was on the worksheet, but when you have sine squared of theta times cosine squared of theta, what you can do is rewrite it as sine of theta times cosine of theta all squared. So we can rewrite this as 81 times integral from 0 to pi over 2 of sine of theta times cosine of theta squared. And so why is that useful? Well, sine of theta times cosine of theta, that can be rewritten as, let me think what color I want to use. Maybe I'll use orange. So sine of theta times cosine of theta, that's the same thing as 1/2 times sine of 2 theta. And so if we rewrite this, we have 81 times integral from 0 to pi over 2 of 1/2 times sine of 2 theta squared. So let's go ahead and square that. So that's going to be 81 times the integral from 0 to pi over 2 of 1 over 4 times sine squared of 2 theta. So we can factor out that 1/4, but we're still not totally in the clear for this integral because now we have sine squared of something. And so how do we find sine squared of something? Well, again, we have an identity we can use for that. So sine squared of 2 theta, this is another one that we talked about, I think, in the previous video. That's going to be equal to 1/2 times 1 minus cosine of 4 theta in this case. So if the, whatever the input is here, you want the input here to be twice it. So if it's 2 theta, then it's 4 theta. All right, so let's put that in and see where that takes us. So now we're going to have 81 over 4 times the integral from 0 to pi over 2 of 1/2 times 1 minus cosine of 4 theta. I know this is a long integral, but we're getting there. So now we can pull out the 1/2. So we have another new fraction outside. So let's rewrite this as, let's pull out the 1/2 and then let's split this into 2 integrals. So we're going to end up with 81/8 times the integral from 0 to pi over 2 of 1 d theta. And then we have minus 81/8 times the integral from 0 to pi over 2 of cosine of 4 theta d theta. So now we're almost done. So the first one, what's the antiderivative of 1? It's theta. So we're going to have 81/8 times theta, and theta, we're going to have to evaluate that at pi over 2 and at 0. And then for this next part, so what's the antiderivative of cosine of 4 theta? Well, you could use a substitution, but just to avoid having to do a substitution and change the bounds again, this is one of the ones that I mentioned. I think it's nice if you can figure out how to do this one in your head, right? It's not sine of 4 theta, because the derivative of sine of 4 theta would give you 4 times cosine of 4 theta. So it's actually sine of 4 theta over 4. And we're going to evaluate that at pi over 2 and at 0. Okay, so almost done. So now we have 81/8 times pi over 2. And then 0 would just give us 0. And then here we have 81/8 times, so here we're going to have sine of 4 times pi over 2. What's 4 times sine of pi over 2? That's going to be 2 pi. And then I'll just write in, I think it's just, when you're dealing with trig functions, it's a good idea just to write it down, plugging it in, even if sine of 0 is going to be 0, but like cosine of 0 is not 0, right? So it's better to not just assume that everything is 0. And in this case, actually, sine of 2 theta is also 0, right? Because if you go to an angle of, I said 2 theta, I meant 2 pi. If you go to 2 pi and 0 are coterminal angles. And so both of these are going to be 0. And so we're just left with 81/8 times pi over 2, which is the same thing as 81 pi over 16. All right, so that is it for this video. Like I said, in the next video, we'll see how some other types of integrals where we'll still be dealing with square roots, but we'll be kind of switching up what's being subtracted from what, and sometimes they'll be added, and we'll see that there will be other trig functions that we can substitute in those cases. So I'll see you all in the next video.